Thank you very much for having me. I'm embarrassed to say that I am not capable of speaking to you in French. So if something I say needs to be said again, just let me know. I'm sorry about that. Okay, so I won't assume that anyone knows what diffusion Monte Carlo is. I'll explain that in a second. Yes, this is joint work with Martin. So what do I mean by diffusion Monte Carlo? Well, so given some underlying Markov chain, so I'm going to be interested in computing averages with respect to some underlying Markov process. Okay, and I'll point out in a bit what particular problems you might be interested in looking at with this method. But let me just describe first abstractly what you can compute. So given some underlying Markov chain X, this scheme, and I'll tell you how in a second, but this scheme is going to generate it takes every step you move forward an ensemble of particles. So what are particles? Particles are copies of this Markov chain. So instead of simulating, if I wanted to compute this average, one way to do it is to compute a whole bunch of copies of this process X up till time tk, so k steps. I generate many copies of many paths of this process k, for k steps. And then I would compute this weight and the value of this function f for each of those paths, and then sum them up and divide by the number of paths. And that would give me an estimate of this number. So that has nothing to do with diffusion Monte Carlo. That's just the simplest possible way to compute this expectation. We'll see that there are reasons not to do it that way. So most importantly, that if you try to compute this average in that straightforward way, then these weights will be very divergent. So many times, for many problems, these weights will be 0 until all of a sudden you get a sample where the weight is huge. Okay, so the variance of the scheme, its quality as an estimator, that simple scheme, is very poor. Okay, so what's another approach? Well, this other approach, diffusion Monte Carlo, is going to again generate multiple copies of the system. But instead of just being independent trajectories, they interact with each other. Okay, so, and in fact, instead of having a fixed number of copies of the system, copies of X, the number of copies is going to be random. So, and the final statement on consistency of the algorithm, so why does the algorithm work? Well, at time tk, I have nk, a random number of copies of the system, with this property, that if I were to sum the values of f on all of my copies of the system for however many particles I have, however many copies I have, then the expectation of that random number would be the expectation we're trying to compute. Okay, so I'll tell you now how you generate that ensemble, how these copies of the system interact. So it's really two steps. So if you imagine that at this point, I've used this algorithm for some amount of time, and at this point, I have some numbers of copies of my underlying system, my underlying Markov chain. What am I going to do? In the first step of the algorithm, I'm going to just evolve them forward one time step. Okay? So I have a bunch of points. I have the transition. I have the rule that generates the Markov chain. For each of these, for each of these copies of the system, I independently move forward one time step. Okay? That's easy to do. You can think of that as just a black box. And then in the second step, I look at each of my samples and I weight them by this number. What is this number here, this weight here? It's exactly the factor that you multiply by in this path weight at each step. It's the amount of weight you accumulate in each step. So each of my copies of the system is going to get weighted by this number. And then I'm going to basically throw out copies of the system that have a very small value of this number and copy particles that have a large value of this number. So I'm replacing the weights by copy number. Okay, so let me give you, if that's not clear, let me give you a picture. So suppose that this somehow represents e to the minus v, okay, for a single step. I have a bunch of unweighted copies of the system. In this case, just one, you'd think of them as 1D. In the first step, I just let them diffuse. Let them take each an independent step of the underlying evolution. Then I attach the weights. The weight here is represented by the size of the ball. So this guy is in a region where that weight is large, and these guys move to a region where the weight is small. Okay? Then in the next step, and I'm not telling you exactly how I'm doing that yet, but in the next step, basically, these guys had small weights. They're likely to drop out of the to be killed, and this guy with a large weight, he's likely to be replaced by many smaller weight particles, so that everybody again has equal weight, and we go back up to the top. Okay? So without telling you exactly what the rules are, that's the philosophy of diffusion Monte Carlo. And this was popularized in the 70s and 80s as a way to compute averages with respect to the ground state of a Hamiltonian. So if this is the solution to the imaginary time Schrodinger equation, then I have this Feynman-Katz formula. You'll notice that this is unnormalized. So this is really the solution to that parabolic PDE. Okay? If I want to compute the average against that solution of some test function f, well, there's a Feynman-Katz formula that tells me that's equal to this expectation where w is a Brownian motion. So if I look at this expectation and I think about discretizing this integral, I get something that looks just like the number that I told you could be computed with diffusion Monte Carlo. Okay, so there's a lot more that goes into what's called quantum Monte Carlo, but this is the setting in which the algorithm was popularized. So it actually was around earlier than that. In the 1950s, people were using something very similar to the steps I've described to sample self-avoiding random walks. So I say that you can think of that as a rare event simulation application. Well, why is a self-avoiding random walk a rare event? If you think about sampling a regular random walk and then ask how many of those are self-avoiding, so a regular random walk of some length n, and then on a lattice, and then you ask how many of those are self-avoiding random walks, the number will be a very, very small fraction. Okay? So you can think of that problem as really a rare event simulation application, and like I said, they used an idea similar to what I've just described, and we'll talk about rare event simulation more in a second. Okay, but it's spread into a lot of applications, this basic idea. For example, if you've heard of a particle filter, so the way that would work is that suppose that I'm interested, so you would never use this for the weather, but just to give you an example. Suppose that I'm trying to predict the weather, okay? And I have an estimate of the state of the weather today, okay? What I'd like to do is, so tomorrow I'll get an observation of the weather tomorrow, and I'd like to update my estimate of the weather given that new observation. So I need to assimilate tomorrow's observation when I get to tomorrow. So the way that you can think about that is that if this is my estimate given all my data of the weather today, then the way I get to an estimate given all my data, which would include tomorrow's data tomorrow, is that I take that distribution, the distribution of the weather today, I evolve it forward. So this is the transition density. This says, given a state of the weather today, how can I sample a state of the weather tomorrow? And then I weight it. Think of this as an observational likelihood. Once the weather tomorrow comes in, once I get my measurement of the weather tomorrow, I have some observational likelihood which I can weight my prediction by. Okay, so the way a particle filter would actuate this formula, so this has nothing to do with a particle filter. This is just a relationship between what's called the posterior distribution today and the posterior distribution tomorrow. So the way you would actuate that by particle filtering is that you'd start with a whole bunch of samples of the weather today, You'd evolve each of them forward until tomorrow. So that means just running your model for each copy independently. And then given a bunch of states of the weather tomorrow, once I get my data tomorrow, I'll weight each of those states by this weight, and then I need to remove unlikely copies and reproduce likely copies. Okay, that's a particle filter. So this basic idea, a particle filter has one additional step which you should really think of as just additional, which is that they typically control the number of particles. So rather than allowing the ensemble to be random, force it to be some fixed number, 50. In weather prediction, 50 might be the example that you can get away with. Okay, so, but that's really, you should think of that really as an additional step. This is the engine. Okay, so to be slightly more specific, but same algorithm. So suppose that I'm at time tk minus 1. I take just to repeat it one more time, make sure everybody's clear. I take my samples at time tk minus 1. I evolve them all forward according to the underlying dynamics to time tk. That gives me these samples xi tilde. Then for each xi tilde, based on this weight, I decide that there's going to be a number of copies of that particle in the next generation. If the weight is small, that n could be small, could be 0. If the weight is large, n will be large, typically. Okay, and in fact, there's really one way to do this that is the only way you would ever do it, but I won't bother to describe that. Okay, and then however many copies I made of particle I, that goes into the next generation. Okay, and the size of my next generation is just the sum of the number of children from each of my particles in the previous generation. Okay? So now let's look at a specific example. So if you remember in the beginning, it was quite a general expectation here. So if I'm doing quantum Monte Carlo, then V really comes to me from the potential in the problem. But in principle, for this, and for this to be true, V can be almost anything. So you might explore other possibilities with V. So here's an interesting one. Suppose you give me some function g, which I'll choose later. So for now, g is just some function. Think of it as a potential. So, and then define this choice of v. So what happens in that formula on the first slide? Well, the sum, it's e to a sum, which telescopes. So you get a simple expression. So now if I redefine f by including e to the minus g, I get this expression. So why is this an interesting expression? Well, first of all, on this side, I have an expectation of the diffusion Monte Carlo algorithm. On this side, I have an expectation just of my underlying Markov process. So why might this be useful? Well, to see why it might be useful, let's think about what happens to the algorithm in this case. So I'm just including the steps that change, and they only change slightly. So the number of particles spawned by the number of particles for the next generation spawned by each particle in my current generation is here. So what happens? Well, when g, if any one particle moves in a way that decreases g, it will cause that particle to be spawned. Okay? If any particle moves in a direction that increases g, that particle is likely to die off. Let me show you a picture how that could be useful. So imagine this diffusion process in a double well. So V is a double well. That means that the invariant measure looks like this. What this thing likes to do is hang out here, and then if you wait long enough, flip over to here. Okay? So there's a number of quantities when mu is small that would be hard to compute by brute force simulation, by straightforward simulation. One would be, suppose I start at -1, and I ask, what's the probability that at time 1 I'm in a set over here? If mu is small, that's going to be very hard to compute. I'll need many, many samples because that probability will be so small. Another quantity that might be interesting, suppose that I'm interested in the average against the invariant measure. So this is the invariant measure. I want an average against this density against a function that's really concentrated around here. So the average of a function that's concentrated around here under this density. That's going to be tough because I'll have for all my computation time, I'll have very few samples that actually wind up in here. Okay? So those are just totally typical rare event simulation problems. So just to help you see a picture of how you could use this idea, well, so for that first problem, okay, that was actually the second problem. Suppose that you're interested in an average with respect to the invariant measure of a function that's really supported on that barrier, on that low probability spot in the middle. What might you do? Well, you might choose a g that looks like this. So if I think of what happens to particles when I choose a g that looks like this, as they move into the barrier, into the low probability region, g is decreasing. So as they move in this direction, they're going to get copied. As they try and slide back in this direction, they're going to get killed. So that's going to force your population to move into this region. Now they can't slide back down this side for the same reason. Okay, so that will give you a lot of resolution in the region that's important for computing averages with respect to f. And f is saying, when I say f is supported on that barrier, that means that what happens out here really doesn't matter for that average. So that's one kind of average that you might like to compute. And this is just an intuitive choice here. This is an artist's rendering of the optimal choice of g. A question that would definitely be interesting to ask, which I think I could tell you the answer to, is what is the optimal choice of g if this was really your problem? Here's another problem. Suppose this is the problem where I start near -1, and I want to compute the probability that I'm over near 1 at time 1. Then I might choose a g that looks like this. So again, g is decreasing as I force myself up to the barrier, to the top of the barrier. But then as the particles want to slide down the other side, they're just allowed to. They won't copy or kill. Okay? So hopefully it's clear how one could use that. So now a reasonable question to ask is what happens to this scheme that I've just laid out when the time step goes to 0? The time step in the discretization goes to 0. Okay? Certainly you should hope that your algorithm doesn't care. So what happens? Well, so if you're thinking about that kind of a question, the most reasonable setup is to think of your algorithm actually as generating a measure-valued Markov process. So this is the measure. It's integer valued. Here's the dt is a parameter for the step size, and the subscript is the time step. Okay, and this is just what you'd expect. So, natural question. Does this converge to some meaningful continuous time process as the step size parameter goes to 0? If it doesn't, maybe this isn't such a good algorithm, even though it intuitively was appealing. So, okay, so the first thing one would do when asking that question, I think it's for a lot of people anyways, the first thing they would do, you see what happens, you look at the generator of the process, of this measure-valued Markov process. And for measure-valued Markov processes, this is a typical choice of test functions. So I've written it in a bit of a confusing way here, but just think of you pick some test function h, and you look at its product over the whole ensemble. Okay? Another way to write that is that it's e to the integral of log h against this measure mu. Okay? That's just for looking at branching processes, that's a pretty typical thing to look at. So this kind of calculation, looking at this difference, would be the sort of thing you'd do to look at the generator of this process and see what happens when dt goes to 0. Okay? If you're asking questions about the continuous time limit, again, probably the first approach you try. So I've done this for you. And what you get is, well, just the generator. So this is just, L is just the generator of the underlying Markov process, the limiting Markov process. So remember, we're looking at this random walk. Okay, it's a biased random walk. Xi, let's say, has mean 0 and variance 1 and are independent. But I don't want to specify any more about Xi. There's many choices of Xi that are mean 0 with variance 1. We'll see. So remember that, because that will reappear in a second. But this is just a biased random walk. We know what it converges to. It converges to an SDE with a constant drift and a constant diffusion. Okay? So we should hope that if this thing converges, the limit should have something to do with that limiting diffusion. So, but when you look, so you do see L. L is the generator for that limiting diffusion. So that's good. But then you get this other term. What's the problem with this other term? Well, LG is fine as well. But here we have this 1 over dt, 1 minus h, this guy. This guy is a problem. So what is delta g? Delta g is the increment of g. Okay, so it's g of x1 minus g of x0. So that's typically, delta g is typically of size square root dt. Which is okay because when I take the expectation, I would normally kill that square root dt term, unless dg happens to be multiplied by the indicator that delta g is greater than 0. Then I'm in trouble. Okay? So something is troubling here with this algorithm. Let me tell you how we're going to modify the algorithm. So this is a problem, and I'll show you in a second that this is a real problem. That the algorithm that I've explained to you does explode as dt goes to 0. It has no meaningful limit from the point of view of the original process. Okay? So, that's not fictitious. That's real. So let me first tell you about, before I show you the plot of that thing exploding, let me tell you the solution. So what we do is we borrow an idea from these restart and DPR algorithms. So the way they work, they're discrete time algorithms. They work a bit differently. They partition space. Okay, so you take your whole state space and you chop it up into sets. And then each set, what happens when you, so I'll just give you the outline. What happens when you cross into one of these sets, when a single path crosses into one of these sets, is that it's split some number of times. It's copied some number of times. The key idea that we borrow from these algorithms, so that's true of all multi-level splitting algorithms. The key idea that we borrow from these algorithms is that they have a way of controlling which particles can go backwards. Okay? So here, this is the parent particle. It comes up to here and it gets split some number of times. Then it comes and it's allowed to cross back. But you see its children, this one, and eventually everything that spawned off of this path, they are not allowed to cross back. Okay? So we want to borrow that key idea. And that little change will end up having a big effect. So let me just walk through, since we've seen these steps for regular diffusion Monte Carlo, let me walk through what the change is in the algorithm. So we take our state space, which was just whatever was the state space of the underlying Markov process, so say the weather, and we add a real number, which we call a ticket. And so now the state space is one dimension bigger, but that doesn't matter. It's no big deal. The main difference is that now here's my rule for copying and killing. So as long as this weight exceeds the ticket value, then I'll survive for sure. So before, any time that v was positive, there was some chance of dying, some chance of that particle being removed. Now, any time that this number is bigger than the ticket, this minimum ensures that that particle survives. So I've removed a bit of the noise here. Okay? And if it's below the ticket, there's no choice, but that particle is removed. Okay? Otherwise, it's basically the same. Now, what I need to specify, though, is the rule for the tickets. I've introduced another dimension. I need to tell you how that dimension evolves. The rule for the tickets is that they should be generated uniformly, so this is not going to be intuitive, but uniformly between what is 1 over the weights and 1. So you only would generate a new ticket when this number is less than 1. Okay. There's a rule for generating the tickets. That's all that matters. every time you generate a new particle, he needs a new ticket. And the initial ticket should just be uniformly 0, 1. OK, so what you should think of is that we've somehow squeezed a bit of the noise out of diffusion Monte Carlo. And let's see if it matters. So going back to that same example that I was showing you before, but now being specific about g. So g is just x. So what am I plotting here? So this is, so I simulate up to time 1, the algorithm, up to time 1, where the time step is dt. I'm always going up to time 1, but now I shrink dt. Okay, and I compute the second moment of the number of particles. So actually the log of the second moment of the number of particles. Okay, you always know the expected number of particles. That comes from that first formula that I showed you by just plugging in f equals 1. But the second moment you don't know. So I'm plotting here the log of the second moment. And you see that as dt goes to 0, always simulating up to time 1, so always doing 1 over dt steps, the regular DMC algorithm explodes. It explodes pretty badly as the time step goes to 0. So that, what I showed you in the generator was not an artifact. It was not just a mistake or something. You really see it in the algorithm. It's a big problem. And then the modification that I just showed you, if I run the same problem, I see it looks pretty good. So what does looks pretty good mean? Well, we can prove bounds like this. Okay, so all the moments of the number of particles are uniformly bounded as you shrink dt. And that ends up being important for proving convergence. So we will prove that you do get a continuous time. We do prove that you do get a continuous time limit. I'll show you in a second. In fact, you get exponential bounds if you can take a compactly supported C. But even if you take something like Gaussian, you do need exponential moments. But even if you take something like a Gaussian, you get this. OK, let's do the same calculation as before. So this is the same kind of test function. Doing these steps for you. Here's what I get for what would be the generator calculation for that process. Looking at the limit of the generators. What I get is, OK, so this term is fine. This term is fine, sort of fine, because it's a delta g squared. So this term is of order dt. This term is a problem again. OK, how do I solve that? Well, now I can just say, which is not great, but I have to say, we'll only consider the domain of the generator will only be functions h, so that, I should have written it on here, but they'll have to, so you have to have h of x, g of x equals 1. Okay, so I have to restrict the set of functions I can look at, which is not good. Okay, for example, if I wanted to compute the number of particles, that wouldn't work. It's not something I can measure with a generator. So that's not good. But it does remove this term. Okay, and this term is delta t squared. So at least there's hope of a limit. But there's two problems now. One is that this is just not including, first of all, this is an algorithm. This isn't, I want to use this thing. V is an artifact. V is a construct. I certainly don't want to say to somebody, you can only measure things that have this V dependence. Okay, any V dependence. So I have to be able to measure things that are not functions of V. So like particle number, like copy number, n. So I don't like that. But the other thing that's a bit fishy is that, well, this depends on the particular definition of Xi. Right? If I tell you this thing has that Xi is there, that they're independent, and that they have mean 0 and variance 1, that still leaves a lot of freedom in saying what this number is. And that's a bit funny, right? Because the actual process, the underlying process, this discretized diffusion, as long as I say that the mean of C is 0 and the variance is 1, it doesn't care about the other features of C. So it's a bit bothersome that it looks like this generator, the limit of the generator is wood. Okay, but again, at least you can see that the really bad term you can get rid of. But because of what I just said about the limit of the generators, it's not really the way to go. So that standard approach of looking at the generators and taking their limit, that standard approach of trying to construct the limit of Markov process is not the easiest way to go. So instead, we construct the limit basically by hand and then show that we have convergence. And the limit, it turns out, doesn't depend on the fine details of CK, which is good. In fact, it's a very intuitive object. You just take, so it's a recursive construction. So imagine taking a single Brownian excursion. So you pick some level, you start your Brownian motion, and you stop it when it hits that level. Okay? And then go on to that Brownian excursion and walk along the Brownian excursion, sprouting new Brownian excursions as you walk along. Okay? And keep doing that recursively. Okay? That's how you build this limiting process. And as I said, it doesn't depend on the details of CK. It's a nice process. It's Feller. It's a Feller when you build the Markov process from that. So the Markov process has to be built from that and is built by basically, if you imagine that as a fan, which is what we call it, Brownian fan, and then you slice in time, that slice is the Markov process we built. And that's a nice Markov process. So the point is we made this small modification of the algorithm, and then looking in the continuous time limit, we get this really nice process. For example, so it's also a kind of interesting process. And I should say that you know, the continuous time limit stuff really, Martin should get the credit for that. So, but let me say one last thing about it before I move on. It's a really nice process. So it has, for example, the copy number, the number of the size of this measure is has at any finite time has exponential bounds. So it has exponential moments bounded. So that's interesting. But even though it has bounded exponential moment, it in any small interval of time, it will actually, there'll be a time where it's infinite with probability 1. So there is some, in any interval, there is a time where the thing blows up. But it blows up really quickly. So what's happening is you sprout. Remember, these are excursions. If I draw the level sets of G, I'm starting from here and coming back to the level set of G. Right? This is my little excursion. What's happening is that I'm sprouting at these special times. I'm sprouting tons of particles right here. But they're really close to the boundary. So they die immediately. So they don't really show up in your workload. Okay. So now, what was the reason for choosing the rule for generating the tickets that I showed you? Well, the same formula that I showed you in the beginning still holds. So this is a consistent algorithm. If I take the expectation of this random number that's generated, it will be the number that I wanted to compute. So it's just as correct as the original DMC. So regardless of regime, so I've spent some time on the continuous time limit, but regardless of the regime, regardless of the problem you're trying to solve, this algorithm always has lower variance than regular DMC. And that's not so hard to see once you realize that if you go through this new algorithm, and at each time step, each time you go through those sequence of steps, you randomize the tickets, then you get the original DMC. So that allows you to compare them fairly easily, and you find that no matter what situation you're in, the new estimator has lower variance than the old estimator. Okay, and as I said, the cost is found just by setting f equals 1 here. That tells you the expected number of particles, okay, at any time. So the expected cost is the same. So it doesn't matter what you're doing, new algorithm better than old algorithm. So let me say one other thing about the continuous time limit, which is that with regular DMC, and this is often pointed out, you don't have to do the killing step, the copying and killing step, every time you take a dt time step. Why not take order 1 over dt steps before you do the copying and killing step? Well, you can do that, but first of all, you'd have to get, in practice, it wouldn't be so easy to get a feel for that lag parameter. That's first, because remember, you're looking at some awful problem where v may be awful, but certainly the underlying process is really, you don't know much about it. And the other thing is, well, we have this result that says, look, no matter what situation you're in, you're wasting variance on the old algorithm. So don't do it. And how much variance you're wasting really depends on the particular problem. OK, so let me show you some examples. Here's a only slightly, bigger rare event simulation problem. This is still very much a toy. These are 2D, what are called Lennard-Jones particles. So this is just a little cluster, a 7-particle cluster. And what I'm interested in here, roughly, is the event that this blue atom, or particle, switches with somebody in the shell. Anybody in the shell. Doesn't matter who. So there's a lot of ways that could happen. Okay? And I could go try and work out each way that it could happen and then make a really smart choice of design for my algorithm. But, but that's not practical on anything more than this problem, so we won't do that. So this is the Lennard-Jones interaction. So these particles, they just feel this. It's the same equation that I showed you before, that overdamped Langevin, where v is given here, and x is the position of all the particles. So what do I do? Well, I'm doing rare event simulation, so I'm going to think about a v that looks like this. I'm going to choose a g that's not terribly smart. Okay, like I said, I could make a much smarter g if I really understood all the possible ways that this event could happen. But I don't want to do that. I'm just going to choose the kind of thing that you'd actually choose in practice. You pick some distance, and that's what you use. Okay? So lambda is up to me. Lambda is a user-defined parameter. Mu is basically the temperature. So this is the minimum from anybody in the outer shell to the center of mass. Okay? It's the minimum distance from the outer shell to the center of mass of the whole cluster. Okay? It's not the only choice that can be made. Clearly, if that distance is small, then somebody that was originally in the outer shell may have moved to the center. Okay? So I'm actually, just to make things easier, I'm going to use that as a proxy for the event. So what I'm going to compute actually is the probability that at time 2, this overdamped Langevin, this diffusion process, the state of the diffusion process, is actually in B, where B is defined by this function g. So that's a little bit of a cheat, just to make things simple. But it's a toy anyway. So these are just the results. So this is decreasing temperature. Lambda, as I said, is something that I choose. I choose it basically so that if I start the algorithm, the diffusion Monte Carlo algorithm, with a single particle initially, that I expect at time 2 a single particle to be in the set B. So if I increase lambda, I can make more particles end up in B. If I decrease lambda, I can make it if I decrease lambda enough so that it's 0, then it's just the original process. And it's very unlikely, that's the point, it's very unlikely that any particle will end up in B, that the process will actually move into B. Okay? So, but I don't do that very carefully. That's just very roughly estimated. Okay, and so that's my only real free design parameter, other than the entire form of G. And then I compute an estimate using the algorithm of that probability. So you can see, so what do I have to worry about? Suppose I chose lambda huge. Okay? Then I would cause any movement towards the center from the outside would cause an explosion in the number of particles. What's the danger? So that sounds good. I would end up with many, many samples in B, which sounds good. What's the danger? The danger is the cost. The cost has exploded because I have to evolve all of these particles that I'm sprouting. Okay? So I have to watch out for that, which means it's not really fair to compute a variance for this algorithm and compare it to the variance for brute force. Brute force could potentially be doing much less work. So the fair comparison is to compare the variance of the algorithm times its workload. What's that? That's like the expected number of particles generated. Well, it's the total number of times I evaluated the potential, the underlying potential, the Leonard-Jones potential. Okay? Scaled by dt. So this comparison is a fair comparison. And what you see is that, okay, you're winning but not by much when mu is larger. You're still beating brute force by a little bit. And as you get to very small temperatures, very unlikely events, the variance times the work, you're winning by quite a bit. So the ratio of these two is roughly how much less work you have to do. Okay? So now, just one caveat about these numbers down here. You know, it's really not possible to be sure about numbers of this size. So, you know, the one rule of rare event simulation is that if you manage to make the event likely, you've made the bad news, all the stuff that can go wrong, even more unlikely. So when you get to probabilities like that, you don't know. Right? There could be, what would go wrong? Maybe it's useful to say that. What would go wrong is that somehow the process takes some other path, and you see an explosion of particles. So it's a very unlikely path, but the contribution is enormous. It would have to be a really big explosion of particles. But what's that? It's okay? Okay. So, okay, so that's a rare event simulation example. Let me show you a filtering example, and then I'll stop. So this is Lorentz 63 with stochastic forcing. Okay, it's very much a toy, but it's one that people play with in the filtering literature. So, but I'm actually going to take a particularly easy example of the filtering problem because I'm making a slightly different point. So I'm going to be looking at continuous time filtering. Okay, so the observations are coming in continuously in this form. Okay, you can see this is a plot of the observations. So the trajectory is actually this trajectory. This is the trajectory plotted in 3D. I want to reconstruct this from these. Okay? And really, what I want to reconstruct is the posterior distribution, the conditional distribution given the observations. And in fact, I'm just going to show you the mean. Okay, so you need a slight modification because you want to control the number of particles in the scheme. This is the same algorithm I showed you before, but here I've replaced the e to the v by a normalized version of e to the v. So this will hold the number of particles roughly close to n bar, if I've written it right. So, but otherwise, really, it's the same algorithm I showed you. So let me show you the reconstruction. Here's the reconstruction with 10 particles. Fine. It wasn't that hard of a problem. But let's look at what a regular particle filter would have done. Diffusion Monte Carlo. It would have given you this. And if you were a person that uses a particle filter and you saw this picture, what you would think is, I need to be more clever about the reference distribution I'm using in each step. I need to use some more clever way of proposing a step, of making that predictive step that somehow incorporates information from the next observation. I've worked on stuff like that. That's what people in particle filtering work on. That's what would be your gut reaction. What these two show you is that that's the wrong reaction. This is just an issue of having spurious noise that should just be wrung out of the algorithm. Okay, you don't need any fancy filtering technique. You just need to put less spurious noise in the algorithm. And okay, so so one thing I didn't, okay, so that's pretty much everything. One thing I didn't tell you about the rare event problem was that that was with the modified diffusion Monte Carlo, the improved algorithm, because I never could have run it with the regular algorithm. It would have been a mess. So this one I do the comparison, and let me point out that this is, so as I said, this is not a hard filtering problem. Usually what people do is they'll remove one of these, so it's partially observed, and then it becomes a bit trickier of a filtering algorithm. Then you might need some fancy ideas, but those fancy ideas should be built upon the right particle filter. Okay, so I was going to talk to you about something else, but I decided that I think that's too confusing, so let's